we're fortunate to have a real expert in the room who's also going to be a co-author on this book as one of the chapters. Alqamah works with us here at the Science Coordination Office and is a great leader in exploring air quality and deep learning. Has tons of really interesting, exciting papers, and we're very fortunate to have him spend some time with all of the busy work that he's doing in this space to present some of the really exciting research. So the floor is over to you, Alqamah.
Thank you, Tim. Thank you for providing me opportunity to present here. All right. Today I'm going to discuss about utilizing deep learning to improve trace gas and particulate matter estimation. I'm Alqamah Sayeed. I'm a surveyor air quality scientist. So let's move on to my presentation. So air quality, as we know, is influenced by a complex interplay of pollutants such as ozone, NOx, sulfur dioxide, carbon monoxide, particulate matter, etc. These pollutants mainly originate from diverse sources and undergo integrate atmospheric reactions, therefore making an accurate forecasting a challenge. We have traditional numerical models that have been instrumental in predicting air pollution levels, but they often need help with high variability and non-linear nature of the atmospheric process, as you can see in the cartoons next to the text. This is where deep learning comes into play, where we can utilize its algorithm to make the estimates better. So our objective today is to explore how we can harness deep learning models to enhance the accuracy of pollutant forecasts derived from the numerical models. By integrating advanced machine learning techniques with the established atmospheric model, we aim to improve the predictive capability and develop more effective strategies for air quality management. In this presentation, I've compiled few of my researches examining how we can utilize deep learning models can be used for the better estimation of ozone and particulate matters. So jumping to my first research, this research is supported by Science SCO for the Southeast Asia region, where we downscale air quality forecast from GEOS-FP model using advanced machine learning algorithm. In this research, we developed a deep learning framework to downscale GEOS-FP PM2.5 forecast from native 25 kilometer resolution to a 5 kilometer resolution. The methodology include two different set of deep learning models. The first model bias corrects the existing forecast by training on the collocated GEOS-FP metrology and aerosol mass concentration. As you can see in the figure on the left bottom, we used different metrology like wind speed, surface pressure, specific humidity at surface specific humidity at 500 hectopascal level, surface temperature, and temperature at 500 hectopascal level. In addition, with the aerosol mass concentrations from black carbon, dust, organic carbon, sulfates, and sea salts. So these all goes into training the model with the surface measurement from ThaiPCD. We train a deep learning model to get a PM2.5 estimation. This estimation is then used. Let me use the pointer. This estimation is then used at each grid from the GEOS-FP model to estimate to bias correct the PM2.5 forecast. So GEOS-FP, just a little background, GEOS-FP is a numerical model that has up to 10-day forecast at 3-hour intervals for various metrology and pollutant concentrations. We are trying here to bias correct and downscale GEOS-FP based model. So once we have a bias corrected grid-wise PM2.5, the next step for us is to downscale that bias corrected PM2.5 model to a 5 kilometer resolution. But the major challenge in downscaling is non-availability of pair of coarse resolution input and high resolution output. So in order to overcome this issue, we designed a novel method where we upscale the existing model to 125 kilometer resolution grid, and then now we have a pair of coarse and fine resolution, as you can see in the step one process, pre-processing step of the model development. So once we have a pre-processing data set, we use 80% of the data set for training and remaining 20% of data for model evaluation. This 20% data set was never used for the training of the model. So once we have an input and a target pair, we train the model. So this model will have a 5:1 downscaling capability. Now, once we had this trained model, we use this trained model for downscaling a 25 kilometer or 0.25 degree lat long grid to 0.05 lat and 0.625 long grid size. So in this way, we achieved a 5 kilometer resolution bias corrected forecast of PM2.5. Here are some results and performance evaluation of the model. In the left, we see a scatter density plot for the all different models. So top left is GEOS native 25 kilometer resolution scatter plot. On the right, on the top is a GEOS downscale or 5 kilometer version. Then at the bottom, we have the bias corrected 25 kilometer version, and the last plot is 5 kilometer version. As we can see that the original native GEOS has a high bias at the low value of PM2.5 and underestimation at the high values of PM2.5 as well, which was corrected by the bias correction model in the step 1, and we have a very close density at the 1:1 line. Once we downscale it to 5 kilometer resolution, the bias correction was consistent enough, and we achieved similar Pearson correlation, index of agreement, and bias in RMSE. In the middle panel, it's Pearson correlation at station location for the ground measurements. We can clearly see from the native 25 kilometer resolution to 5 kilometer bias corrected resolution that model was performing very well on each of the station locations. Similar goes for the root mean square error as well. Since this is a 3-day forecast, I wanted to highlight how well the model performs up to third day of the forecast. On the left, there is a tabular statistics for the model performance, which we can see that for all 3 days, the DNN model was consistent in forecasting PM2.5. On the right, on the top, it's a day 1 forecast time series from March 1 to March 31, 2020 at Nakhon Dachshima Municipal Water Waste Plant pumping station. Blue and green line are GEOS PM2.5 estimate at 5 kilometer and 25 kilometer respectively, and orange and green lines are DNN estimated PM2.5 at 5 kilometer and 25 kilometer respectively. The gray color shows the ground measured PM2.5. As you can see in the day 1 forecast, that DNN model was very good in reducing the high biases. If you could see the third day, that there is an underestimation from the native GEOS model, which was corrected by the DNN model. For all the instances of underestimation as well as the overestimation, although the time series didn't perfectly match with the original time series, but it's close enough to the ground measurement. Here it is a sample snapshot of PM2.5 estimate over Mekong region. It shows all 4 model as we were discussing in this talk. The plot on the left shows 18-hour ahead forecast that was initialized on April the 3rd, 2021 at 1:30 UTC. I have zoomed in a small portion in the middle of Thailand where GEOS 25 kilometer version was overestimating PM2.5, which was very well bias corrected by the DNN model and the downscale version of the model. You can clearly see that how well the boundaries are now defined for all these station location points. Here is another example. On the left, there is a 3-day world view image, direct RGB image from the world view website for the viewers. satellite. You can see the smoke plumes on the 1st April and the 2nd April and the 3rd April. There is a little bit of cloud. This animation shows a consistent performance with the various RGB images. So to conclude, we developed a DNN model for bias correction that improved the forecast for 3-day PM2.5. We also developed a CNN model for downscaling that achieved 5-kilometer spatial resolution, which was consistent in spatial pattern with various RGB images, and also consistent with the 25-kilometer estimate and the observed PM2.5. The next step for this research is to integrate this into SERVIR Southeast Asia Air Quality Dashboard. Currently, the dashboard has only 25-kilometer version, as you can see in the bottom right image. I have the link to the dashboard where you can click and see what kind of data we are producing. For the future work, we are trying to implement applied DNN model bias correction at 5-kilometer resolution as well. But the challenge for this is that we need to downscale the DNN input parameter as well. So moving on from this to the second research, this is a machine. This is a research we did for a HeyCast Tiger team project. In this research, we developed a machine learning algorithm to estimate PM2.5 from GEOS-R satellite AOD. This product was developed in collaboration with the NASA HeyCast Tiger team led by Dr. Pavan Gupta with several partners from US EPA, NOAA, University of Alabama at Huntsville, University of Wisconsin, and USRA. So in this, so first a little bit brief about GEOS-R series. So GEOS-R series is a set of geostationary satellite goes east and goes west, looking at the US from the east and west respectively at all times during the day. So for the first step in this project was to combine the data coming in from goes east and goes west and evaluate it first. So NOAA already produced a PM2.5 called geographically weighted regression algorithm, which use AOD and produces PM2.5 based on GWR algorithm. We utilize this GWR algorithm in conjunction with the surface-based measurements and NOAA's numerical model, HRR, which forecasts meteorology. So a little bit more detail about this model. On the right, you can see a model architecture here where we have 5 fully connected DNN layers. The input for the model was wind speed, relative humidity, and 2-meter air temperature from the meteorology. And from the GEOS-R, we used AOD, smoke dust mask, and GWR estimated PM2.5. Then we trained a neural network model from the AirNow PM2.5 network. And then once we have a trained model, we use that model to estimate PM2.5 at each grid location from the combined GEOS grid. To do that, we initially splitted the data set into 14 boxes as shown in the figure here on the right bottom. This was done so as to have regional quality for the model. For this study, we also used a customized loss functions based on index of agreement, which showed a better performance than traditional loss function like mean square error or mean absolute error. For customized loss function, I have a separate paper I wrote. You can find more detail on that about the index of agreement based loss function in that paper. Here are some state-wise result performance metrics. So the top row is index of agreement, middle row is Pearson correlation, and the bottom row is root mean square error. And the columns are different. So the first column is GWR algorithm estimated PM2.5. The middle column is DNN estimated PM2.5, and the last column is the percentage change from the base GWR model for each state. So for each state, all known data points were aggregated and the performance metrics were calculated and then put on a map. As you can see from the percentage change map, both IOA and R are increasing for all these states. There are no state where we have a performance decrease in a performance. That same thing can be said for RMSC, where we see a decrease in root mean square error for all these states. So here is a snapshot animation of graded PM2.5 from GWR in terms of AQI and absolute concentrations for August 30 during Canadian wildfire season, when we had orange sky over New York. So you can see that plume coming in from north over the US for the 3 days continuous, and then it stopped on 31st August, which was very well captured by this animation. Sorry, this animation is not working right now. But it was very well captured by the DNN model, and it was also able to bias correct several of the points where GWR model was overestimating. So to conclude that, we developed DNN models that shows a 3% increase in index of agreement, 5% increase in Pearson correlation, as well as 18% reduction in root mean square errors. When we evaluated this data set over an independent data set from Jan 1, 2020 to June 30, 2020, that's peak COVID period, we found that the model performed much better than the GOES GWR model. We also evaluated this model for a whole year of 2022, where we found out this model again outperform base GWR model. So next step for this project is that this framework is now integrated in NOAA operational network. So we will be able to get operational near real-time PM2.5 estimate from this model. AirNow might also integrate this into their framework as well. We are in talks with them. For the future work, we are planning to completely eliminate base GWR model and just use the AOD from the GOES-R satellite to estimate PM2.5. Moving on, this is third and last study. I don't want to bore you all with different modeling study. So since we know that ground measurements are not gridded and are not spatially complete, in this research, we developed an algorithm to estimate ozone, particulate matters, etc. At 27 kilometer by 27 kilometer over South Korea using just the ground measurement. This research used the partial convolutional neural network developed by NVIDIA for image in painting. For this, since spatially completed observation dataset is not available, we use CMAC-derived pollutant as the proxy for complete dataset. Figure on the left shows process algorithm. First we extracted a 32 cross 32 grid over South Korea from the CMAC run that has 27 kilometer spatial resolution. Then we co-located the ground measurement on this on the grids of CMAC grid. Once we have the location of the station on the CMAC grid, we removed all the unknown points from the gridded CMAC data set, and then also created an inverted mask from these grid that doesn't have data. So this pair of known points and unknown mask acted as the input for the unit partial convolutional model. The modeling architecture is shown on the right bottom. That is a unit architecture which has two layers. One is data layer and one is mask layer, and then general unit architecture for the partial CNN. Once we train the data, so for the target, we use the spatially complete CMAC dataset. Then we train the model. Once the model was trained, we use this model to estimate PM2.5, especially collocated observed ozone, PM2.5, and we get imputed data set with 27 kilometer resolution. Figure in the center here shows CMAC ozone concentration at 27 kilometer grid. Then we had a mask. We applied this mask to get a spatially co-located CMAC grid where we have some known points and some unknown points. And when we pass it through our trained model, we get imputed ozone concentrations, which looks similar to what we have as the true value. This study was published in the atmospheric environment. So here I just want to highlight the power of this algorithm. I tested this algorithm with 2% known point, 3%, 4%, and 5% known point. So for 5% known point, we had an average index of agreement of 0.89 for the CNN, partial CNN algorithm. We compared it with the inverse distance weighting and Kriging. When we gave the model only 5% known point, the CNN performed about 0.9 IOA on an average, and IW had 0.75, and Kriging had only 0.48. When we only provided 2% known points, so for this, we have 1024 grid points. We only supplied 20 known points to the model, and we saw only 2% decrease in performance. We got an average IOA of 0.87 when we had only 2% known points. So even with very less known points, we were able to achieve very good accuracy in imputation. So to summarize this research, the CMSI model developed in this research performed exceedingly well for imputation of unknown grid point with a yearly IOA of 0.94. We did a lot of evaluation, including 10-fold evaluation, independent evaluation, which can be found in the paper as well. We also tested it on other pollutants like PM2.5 and PM10, and we saw a similar kind of performance. We also downscaled this 27 kilometer resolution to 9 kilometer resolution, and then again tested this on all three pollutants, and we found a similar consistency in performance of the model. Apart from that, the model only need about 2% known points to estimate graded data set. So in conclusion, for my talk, numerical models are very good at estimating pollutant concentration, but they have systematic biases, which can be reduced using advanced deep learning models. Since numerical models are physics and chemistry driven models, using deep learning models in conjunction with numerical models will improve their estimation. We don't have to use either or, we can use both for our modeling purposes. Thank you. These are the references I used for this research. I'm open to questions.
Alqamah, that was fantastic. That's great.
Thank you.
Let's open it up to questions. Any questions on the line?
Hello, can you hear me?
Yeah, we can hear you.
Yeah. That's a very great talk. So thank you so much. So I do have several questions. One is about your downscaling application, like the first part, because downscaling is quite very important, like in many applications. So I wonder, do you have any specific process for your model? Because for me, it seems like you directly train your model on one scale and directly apply that model into a new different scale. So is there any different process, or it's just
so the assumption for this doing downscaling on one model and applying it on a different resolution is that physics and chemistry for the pollutants and the trace gases would remain same on any scale. It's just that they are not well defined at the intermediate points. Therefore, we applied this algorithm, and we found out that the model was consistent enough at the final resolution as well.
I see. So basically, it means like you just need to change the resolution for your input, so you can
Yes.
get. But does that means like basically for your application, like the two scales are quite similar? They're just very heterogeneous, homogeneous within the. Okay, I got it.
Yeah.
So another question is about your like. So I just want to have a discussion with you because you compare your model, like a DN model with a GWR model, because we know like GWR model works because it rely on like the spatial autocorrelation, consider that kind of aspect. But DN model does not count that part. But in your case, DN model outperform GWR. So does that mean like spatial autocorrelation is not very important in your task, or do you think like if you can add a similar mechanism into DN model, it can help further improve the model accuracy? Because I saw some papers like they consider like a spatial correlation for the.
So yeah, I agree with you. Spatial correlation is important, and that is the reason why we didn't train one single model for whole US, because US is a big domain, and you see a variability in PM2.5 on the East Coast and the West Coast. So in order to eliminate that a single model would perform for all the points is not right assumptions. Therefore, we splitted the model into 14 different boxes. We can decrease the size of boxes, but we might not have enough data points in smaller boxes to train the model. So in order to have large enough data set to train the model on, we did 1,000 kilometer by 1,000 kilometer boxes here and trained 14 different models. Once we have 14 different models, the other step was to create an ensemble of these 14 different models to have one complete model for whole data set. So this addressed the question of spatial pattern within a small region. But I agree with you that having a region-specific model is much more important than having one single model for all the data points.
I see. So basically, it's just because the data constraint, something like that.
Yeah.
Okay, got it. Thank you so much.
Nice. Any other questions on the line? Oh, go ahead, Meryl.
Yeah, I was curious in the downscaling. I don't know if you go up a few slides back that way. I think you said you initially upscale it to 125 kilometers.
Yeah.
Could you explain a little bit more how that works or why that was important?
So to have a 25 to 5 kilometer training data set, we need a pair of input and output, and having a 5 kilometers, we can do 5 kilometer resolution. We can use GEOS-FP and run a WOF CAM 5 kilometer version and get a data set, and that's a lengthy process. And we are not sure that the performance of WOF CAM 5 kilometer would be good enough for the model as well. And since there will be inconsistency between these two models, so we came up with idea, Pawan and I came up with an idea to upscale the existing 25 kilometer to 125 kilometer. Now we have a 5:1 upscaling. We do a 5:1 upscaling. So once we have this pair of data set where we have 125 kilometer as input to the model and 25 kilometer as the output of the model, we train a CNN model. So the underlying assumption, as I was telling Chisan, if I'm pronouncing your name right, that we assume that the spatially the 125 kilometer and 25 kilometer will have same kind of differences as 25 kilometer and 5 kilometers. Therefore, we did this algorithm design, and then we evaluated model. We were not totally relying on it. We then evaluated model with the ground observation and found out that this model works perfectly fine, and we don't have to get a 5 kilometer numerical model run to train the model. So I hope I answered your question.
Well, I'm still confused, but we can talk later because
Yeah.
I've had a lot of catching
Okay.
up to do in this area.
Okay, perfect.
Alqamah, great presentation. So for this downscaling, I know we worked mostly on the spatial resolution, but there's also the temporal component that we haven't really looked into. So do you think like using some of the algorithms that also take time into consideration would be useful, helpful, or?
I don't believe it would. Means it will help. Any more data would help, but it won't be of much significance because we are comparing one space with another space. We are not comparing one space with another space-time data field. So we are comparing a 25 kilometer space with a 5 kilometer space, but the space is at same time. So adding more time layer won't benefit too much, but it will have a little bit effect on the model performance.
Okay. How about
maybe it may confuse the model a bit because we are adding more time layers.
Yeah, it kind of makes sense on the downscaling part. How about for the first model where we are actually estimating the PM2.5?
So for the first model, we are doing a point-to-point estimations, bias correcting based on the existing meteorological fields. I have tested different. If you use the time series, it is okay to use a time series. But if you don't use time series data, means for the training, it won't affect much since it's a point-to-point estimation bias correction. If we were estimating a 24-hour time series at one go, then it would make much more sense to have a time series data set.
Okay.
Otherwise, if you do a continuous time series, most of the time you will get a repeated time series or a time lag time series, and you get very high performance in that. But that doesn't make any sense.
Gotcha. That makes a lot of sense. Yeah, and not a question, but for the last application where you are imputing many of the missing data sets, I see like a lot of applications, especially in the cloud region for several other applications.
Yes, so this research is, we also did this research for the GOSI AOD, where we imputed the location where clouds were present for the AOD, and it's a separate research we did, and we got a similar kind of performance metrics for that research as well.
Okay. Was there any particular reason where you're using that particular algorithm? Because I know like some other algorithms like GANs, generative adversarial network, those are also...
So yeah, we don't have to go too much complex to make life hard. We can use simpler algorithm. It's not a simple algorithm, but it itself is a complicated algorithm where data array and mask, they communicate with each other, and masks are filled based on data array positions were filled based on mask, and it has 6 different loss function which is used, and it was actually the algorithm was developed by NVIDIA for image in painting. So what they were trying to achieve was that they had an image, and that was washed out image completely, and use this algorithm to fill that washed out image. So I repurposed this algorithm for the air quality estimations.
Awesome.
But anyway, we can use GAN and other algorithms. So there are tons of algorithms which can be used, but we don't have to design a new algorithm altogether for the air quality estimation, because these air quality fields are they are not inconsistent in space. They have a specific gradient. So estimating them in space is a pretty easier task for deep learning models.
Awesome. Thank you so much.
Any other questions out on the line?
Thank you for the talk. Am I audible?
Yeah.
Yeah. Mm-hmm.
Could you go to the downsampling part again?
Let's go to that.
Yes, here. So, in the first model where you are estimating PM2.5, you're giving it a lot of other data like wind speed, pressure at different scales, 10 meter, and a lot of different scales. But during the downsampling, you are not giving it some kind of a prior. I think maybe if we gave it some kind of a prior, like some kind of satellite image or SAR image, it would be able to learn better. Because like what we have in mostly like downsampling kind of thing, maybe the model is learning something that looks good. Like it generally happens in the classical ML scenarios. Model learns things that looks good, but whether they are right or not, as you can't even verify actually, because we know that you did 125 to 25 to 5. We are accepting because it looks good on that. It's a very circular kind of question. I'm sorry. Just wanted your thoughts on it.
So I understand your question. Actually, since we are only doing spatial imputation or trying to find out what is the value within the grid, and we are not just relying on if it looks good. We actually evaluated with the data set with the ground measurement, although we cannot evaluate all the data points, but we can have multiple data points. We have like 82 stations in Thai PCD alone to evaluate the model. But I also agree with you that if we use a different layer of satellite observations or digital elevation from the Landsat, etc., we could be able to improve the quality of PM2.5 estimate at 5 kilometers. So we can definitely use different sources of data, but that making an algorithm more complex and achieving just 2% improvement is not a right way to go for an operational problem.
Yes, definitely agree on that. Thank you.
Yeah.
Any other questions? Well, I have a couple comments and just a few questions. I just want to say, Alqamah, I think this is just a fantastic presentation. The amount of examples that you went through within 30 minutes is pretty unbelievable. You could have done an individual hour talk on each of these publications and efforts. So I think there's such a wealth of opportunities for more talks, obviously, because I know you're working on that stuff right now all the time. And I'm so excited to see your book chapter that I know we're still in the forming stages of that, but there's going to be so much need in the community. So great. And I know that when this video goes live on YouTube, there's going to be so many people coming to it because there's 3 great examples here. So I just wanted to make that comment. And I think also your ability to really distill this information down is fantastic because there's a lot of different methodologies within this presentation. So kudos there. I had a question on, a key takeaway that you brought up on the last example in South Korea with doing this analysis of looking of how much data you're actually providing to the model, 2% to 5%. And I find that to be such a key takeaway for the actual application, because immediately I was thinking about, what's the transfer of this type of methodology, because I'd imagine in data sparse regions, folks are going to want to try and pick this up and use it, and having that sort of inherent knowledge of what is my limitation of existing data will allow you to sort of implement that. So I just have that sort of first question here of like, what is your thoughts on, the next steps of that use case and that example in South Korea in particular, of sort of connecting on how to get that out into the user hand. Go ahead.
For the use case, we were discussing on email as that we are going to implement heat wave forecast using the spatial imputation using DHM's DHM temperature profile, and we are trying to. I will be designing the algorithm from now onwards. So in the use case, we'll use DHM's 2-meter air temperature or the temperature measurements and design a spatial complete data set. And that spatial completed data set, in conjunction with the SERVIR's high watt model, will try to forecast a heat wave across HKH region. So this is work which is in pipeline for that specific algorithm.
That's fantastic. I know there's a huge need for that. So that's really cool. And I think the takeaways that you mentioned of, sort of working with these sparse data sets is going to be key. And I had a question that Chisang, when he sort of mentioned about the sort of the spatial autocorrelation on your second example, I think it was, what were the sort of the nuances in slicing up the 1,000 kilometer boundaries and dealing with those individual models and the sensitivity of those leading toward the ensemble? Because I think this is also very unique in the sense of, I think often in the applied work, we're maybe only focusing on use cases and then trying to make that maybe at a country level, something like Nepal, really focused. But when you're working with these much larger domains, what is a good method for seamlessly fitting these different approaches together? And I think this is really unique.
So there's no specific method which one method fits all in the DL. So the good thing about machine learning algorithm is that you can design an algorithm in a week and test it in another week. So it is really fast application, not like numerical model where you have to design algorithm for months on months and add it to the system and then run forecast for several hours. You can test this algorithm like quickly in a day. So in dividing or slicing the data set, you have to look into the historical data sets of how the air quality parameter or the temperature parameter profile is, or the wind pressure, whatever your target parameter is, how that is behaving in a particular region, and then selecting or devising an algorithm that subset these regions into separate regions. That's a complex algorithm. Shortcut is you can slice them up into a smaller chunks until you have like a reasonable enough data points to train a model. Mm-hmm. So this is an easier approach. Divide the domain into such small sections so that you have enough data point in that section to train a DNN model or a deep learning model. That's what I would, yeah.
And for assessing that also, that's looking at the data that's coming in, but then also sort of making the decisions on what's the stopping point for the quality of that product for the eventual ensemble.
Yeah.
Well, thanks so much. That is fantastic. Really, really fantastic talk.
Thank you.
I'll go out if there's any more questions on the line. All right. Thanks again, Alqamah. Really great. I'm so excited for the work that you mentioned about the stuff in Nepal. I know it's near and dear to many folks on the line, but there's just so much other great work that I know you're doing as well. So thank you all. Fantastic talk again, Alqamah, and I'll see you guys in the office next week. And thanks everybody for coming online.
Thanks everyone.
Bye.
Thank you.
Bye-bye.
See you.
Bye.